This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, we might as well get underway. So, just 2 weeks to go. So we've just got tonight and next week. Tonight I'll probably won't get through both of my subjects that I put slides up for. I might have to finish the other one off next week. But I wanted to start off by saying some general things about video on demand systems, bringing together some of the stuff that we've talked about, in particular the components that go together into a video on demand system. And I thought it might be interesting to have a look at Netflix as an example, the prime example, I guess, these days of video on demand, and use it to pull out some of the, to illustrate the examples of how some of the stuff we've been talking about is actually used in practice, and also to bring out a couple of extra little technical issues to talk about. Okay, so, and then we'll go on to talk about home entertainment and digital TV in particular. So, let's get started with this. So, if you imagine that you're a video on demand service provider, so you imagine that you're the CEO of Netflix, for instance, and you made a list of the sort of things that you'd need to worry about or need to get right, then at least a high-level list might look something like this. So, from the point of view of getting content into your system, you certainly don't want to do this sort of thing manually. Imagine the scale of the task in the case of something like Netflix. You want to be able to automate the ingestion, is the name, is the term that's used, ingestion of the video file or the video and audio file. You need to know all the technical parameters about it without having to sort of type them in. So this is the metadata issue that we've talked about. And you need to know the metadata that will allow your systems to categorize it, and your systems to make recommendations about it, and your customers to be able to search for it. So things like the title and the source and the directors and all that sort of stuff. And you need to also know the business rules around it. That was the other half of the metadata. So what agreements are there about what you can charge for it? How long do your rights apply? So when have you got to take it down from your servers? To be able to publish the content, you need to be able to push it out onto some sort of content delivery system in the right format or formats, in particular formats. because you might have to deliver to different devices, you might have to deliver to different resolutions with different bit rates, and we'll talk about that in the case of Netflix a little later on. And you have this issue about protecting intellectual property rights. So you need to apply DRM systems in some way. The content needs to be discoverable, which is the generic term from the customer's point of view. So whether your customers are searching or whether they're browsing or whether you provide recommendations to them, that's called content discovery, and it relies on that metadata earlier. And if you customize content, so if it's an advertising system, maybe you're doing targeted advertising, or even if it's not, doesn't involve advertising, you probably want to make recommendations, you know, people who viewed this movie also like this one, sort of thing, or set up personalized channels. You want to be able to track customer usage, not because you're evil and want to check on what they're viewing, but that sort of statistics enables you to understand how successful or how popular some of those titles are. Just to know that someone opened a file is not so useful as to know that they opened it and watched it for 2 minutes and then stopped. You need the business systems, of course, to support the transactions, to organise payments and so on. And there's also a whole area which is greyed out here. We're not going to talk about it, which is customer relationship management, which is the generic term used in businesses to deal with customer queries and deal with accounts and all that sort of stuff. It's not media oriented, so that's why it's greyed out. So before we start looking at Netflix issues, let's just think about this generic multimedia delivery system. And I'm going to build it up a little bit as we work through it, because there are other components and it's a little bit overwhelming if we look at all of them together. So this is showing the flow of the content alone. We'll talk about metadata in just a second. And there's probably no big surprises here. Let's work backwards from the customer themselves. They've got some sort of device on which they're viewing the content. It's arrived here having gone over access networks, gateways, a home network perhaps, and we'll talk about some home network issues in the next topic. It would be delivered via a CDN. Certainly any scale of video on demand would demand a CDN, as we've discussed. And that CDN would be dependent on its content from an origin server. So all of that's just about delivery, right? All the back end here is what you're doing within your video on demand system. So so maybe then let's start from the content source. So the content source is the movie studio, Universal Studios or Sony Pictures or something is providing the content. It's encoded in some format to be ingested, but that's not necessarily the same format as you finally deliver. Why do you think so?
Because it depends on the requirement. Maybe bandwidth, rate requirement, maybe the rate, depends on the rate. Maybe you need to compress it a little bit in there and you compress it more in there.
Well, yeah, certainly you're not bitrate constrained over here, so you can have higher quality, but if you're ultimately going to deliver on a lower quality, why would you ingest it at a higher quality?
Higher?
Well, I thought that was what you were saying. You were saying a less compression, so it's going to be a higher quality, isn't it?
More compression than that.
Yeah, but this end less compression, so a higher rate. Yeah. So if you were ultimately going to deliver it at a low rate, lower quality, why would you ingest it at a high quality? Do you think?
To maybe if you need to do more processing, you need high quality. If you depend on the application.
Yeah, no, I think I like the way you're working it out. That's all right. Any other thoughts? Well,
deliver the high quality video to for example, to the 4K TV.
yep. Well, yeah. I mean, you are dependent on these range of networks and this range of consumer devices over here, and they may change over time. So, 4K TVs suddenly become, well, not suddenly, but they emerge as popular. and you've compressed everything to HD. So you've got to go back to the original source and get a 4K version. So ordinarily you would ingest at the highest quality you can, probably barely compressed, or compressed using a very light compression, and you'd make a master copy and keep it as a master storage. So that later on, when you need more rates in your adaptive streaming service, for instance, or you need a 4K version because now 4K TVs are becoming popular, or I don't know, you can imagine the possibilities. You can just pull it out of here and re-encode it. So once you've ingested a copy of this at the high quality, you may actually have to transcode it, so re-encode it at in a common format, because this could be coming to you in different formats, and you probably want to maintain one flow. To actually deliver it, you want to transcode it. So transcoding, as the name suggests, is converting from one encoding format to another. You're not encoding fresh, because this is encoded to some degree. So you're actually transcoding from one format to your delivery format. You might then have to put this through a content protection system, so it's the the encryption and management of keys, before you make it available online. Okay, so that's the main content flow, but associated with all of this is the metadata, which you're also ingesting. So just as you are ingesting the content up here, you're also ingesting a set of metadata which describes that content, and that would go into your asset management system. So your asset management system knows about all your assets. It knows that you've got copies of a particular movie, and it's associated with the metadata that you've ingested over here. So you've got metadata storage up here. And that's the one that's going to control this transcoding. It's going to keep track of, it knows the metadata that describes the technical parameters here, and it tells this transcoder to get this file converted from this format to that format at this bit rate, or these multiple bit rates. Because that knows it stores all the metadata there, it knows all the movies in your collection. So it's also what this application server goes to. So when you're talking to the, use Netflix as an example, you connect into Netflix and you browse through all the titles, you're talking to this application server, which knows all the list of content that's available. And at some stage you're going to say play this, and only at that point do you switch over somehow to this origin server. And we talked about how you would effectively get a URL from this guy, and via the CDN operation you would be connected through to the appropriate closest or best CDN edge server. Now the next addition here is to, if we did personalization and recommendations and so on, we would have to know something about the customer, and we'd have to know something about the assets. So they would come together in this recommendation server. I mean, these are drawn as different boxes, but they may be, these may operate in the same server. This could be where are we? This we'll see in the Netflix case is cloud computing. It's not even a single box. We've got our business processes up there. So this is takes the metadata that describes how long we've got the piece of content, the date at which it can be made available. So we can put it on the servers, but the application server is not allowed to show that it's available, and so you're not able to get any links to it until a particular date. And then after a particular date, you've got to take it down until you renegotiate, if you want to, the rights to show it. Of course, we've got financial systems up there that deal with the dollars, and we want to collect records of audience data and what has been purchased, and that we need to deal with the accounting there. So when we get money because someone's watching a movie, we've got to send some back to the content source. Does that make sense? Is that all okay? Yeah? Okay. So let's look at some aspects of Netflix. I'm not going to, I haven't got access to information about their entire system, of course, but they do publish some interesting technical stuff if you're ever curious. But what are the interesting features about Netflix? And I'm assuming everyone knows what Netflix is. First of all, they're very large scale. They're being a global organisation. They have huge storage and delivery requirements, and so storage and delivery is going to be really important to their business. What's really important to them, again, if you imagine yourself being the CEO of Netflix, the first thing they're going to want is happy customers because they'll come back. So you're going to want to make lots of content available. You're going to want a really easy to use and highly responsive user interface. You're going to want to control quality of service, so you're going to want a fast response time, you're going to want high picture quality, you don't want buffering delays. And of course, price is something that you need to manage, partly for your profit, but also you want to keep your costs down so that you can keep your prices down. So efficiency of delivery is going to be important, and bit rate is going to be important. Remember that you're going to be interfacing to this this huge network, and we've already talked about what proportion of the whole of the internet traffic is actually due to Netflix. They're delivering to a diverse range of devices and across different markets. So they're delivering to I don't know how many countries. A figure of 150 comes to mind, but I might be making that up. I can't remember. But anyway, lots of countries. With different types of infrastructure. So as they enter developing countries, there's going to be more mobile devices than cable-delivered devices. And they also have legacy devices. So what do I mean by that? I mean someone's using what's an example? Well, CRT monitor, yeah. Well, even a standard definition monitor, or an old style box that's been superseded, like a Hulu box or one of these, or what is it, Roku, something like that, Roku. And maybe it's only able to do 720p video, although you've moved on and you're now providing high definition and maybe even 4K. And the other interesting aspect of their environment is how dynamic it is, because it's a lot of it's changing. So the catalogue's changing all the time. Of course, you're getting new content in, and some of it is being expired. You've got growth of customers. You've got to keep tabs on encoding advances, and we've talked about how they are changing quite rapidly. And the changes in the consumer electronics, so 4K TVs and mobiles that can now do HEVC, where that wasn't available earlier. Let's talk about the encoding that Netflix does. So they use VBR, adaptive streaming, exactly as we've described, and they deliver to a wide range of devices. So they need multiple versions of content at all sorts of resolutions and rates and different qualities, partly to deliver to the different devices, but also to allow for the adaptive streaming, so that when the network throughput reduces, they can fall back to a lower rate. And actually, it's my last slide in my slide pack, but I'll show it now, which is this. This is a Netflix plot of actual recorded throughput of an actual viewing session. And we see that the throughput, megabits per second, really does change quite a lot. And of course, that's why we have the adaptive streaming, to go up and down and try to sort of follow that to some extent. But I just wanted to show that to emphasize that this variability of network throughput is not a fantasy concept. It really does occur. So Netflix quotes this example in some of their technical literature, where one episode of the Crown TV series requires more than 1,200 files. Why 1,200 files? Well, I still haven't figured out exactly how we get to that huge number, but you can see the concept here. So for a particular episode, there are video tracks and audio tracks, and they're encoded independently, in the sense that you could have any of these combinations of audio with any of these combinations of video. So they have multiple video formats, and within each format you have multiple resolutions and multiple qualities within those, and you have multiple audio formats, surround sound or stereo, and in different languages, and subtitle tracks, which are separate again. And it's an advantage of the adaptive streaming system that it's up to the client to just pull these together. So if you want to listen in Turkish to this episode of The Crown, but you want the subtitles in Korean, then you just pull those particular files off the server. Anyway, interesting that they can get to such a high number of files. So sorry, before we go there, we'll just understand what I'm wanting to illustrate next. So a question arises about what quality and what resolution they should use at each of these levels, right? Because we've got two parameters, if you like, two axes to work with. 2 degrees of freedom is a better way of describing it. So we can set a sort of quality target based on quantizer that's used in the encoder. And we also can decide which resolution to use. So if we want to increase the overall perceived quality of the image, which do we change? Right? Do we keep the resolution low and increase or decrease the quantization step size? Or do we keep the quantization step size the same and increase the resolution, which gives us better quality? And I want to illustrate the trade-off here with some encodings of some test video that I did at different rates and different resolutions. So I've got standard definition. We're going down the low end so we can easily see the issues. Standard definition video encoded at those bit rates, but also a lower resolution, a CIF resolution. So it's about half resolution in both dimensions at these lower rates. So hopefully, if I can figure out how to get all this working, I'll show you this. And as usual, we've got all sorts of processing going on from the time I generated the video to being displayed on this device and then being converted to that resolution, but hopefully we'll see what's going on. So this is one of the standard test sequences that has been used in MPEG standardization, actually. Maybe I'll just turn the lights off completely because it'll be easier to see. Romantic. And so this is 5 megabit per second and full resolution, H.264. Oh no, sorry, it's 1 megabit per second. Hang on. Didn't expect that. Hang on. 5 megabits per second. And you can see why this is a test sequence. Well, actually, tell me, what do you think are the features about this that make it good for a test video?
All sorts of colors in it.
Yeah, all sorts of colours. What else?
It's moving also.
It's moving. It's got translational motion here of this calendar moving upside down. You've got the up and down. Sorry. You've got the rotation of the ball. You've got the movement of the train going in one direction. You've got the calendar going in another. And it's also panning at the same time. So you're panning across this background which has very sharp edges. So it's horrible from the coding point of view, right? It's quite challenging. I should have discovered how to loop this thing. Anyway, never mind. Anyway, just have a look through you. That at 5 megabits per second, there aren't many coding artifacts. You can maybe see a little bit of sort of noise on this complicated lamb's wool thing, but the artifacts we mainly see are interlacing things like this. So let's go down in rate. So exactly the same resolution, but at 2 megabits per second. And what can we see there? We can probably see a bit more of the... If you look at this lamb's wool, you start to see some noisy bits there. And the other thing we see is, maybe if you have a look at this, inside this ring, I'm noticing it there. What do you see there? Sorry?
Don't see any difference.
Can't see? Oh, you're looking too far away, obviously. What I'm seeing up close, anyway, is that it's... Pardon?
There's some tables.
Some blocks.
Yeah, some blocks.
Yeah, but the interesting thing is that they're not being updated every frame. Yeah, see that? It's they're being updated now. So why do you think that's happening?
Developing packet or using packet?
No, all the
Chop off
all,
the thread.
pardon?
Chop off the thread.
Can't hear.
Chop off the thread.
Drop off the line.
Oh, block. Well, it's all blocked. I don't understand. What happens about that often? Don't.
Sometimes it runs out of
Dropping maybe the
No, it's not.
P and B.
You're getting close.
Because it is
Dropping some
coding at a low bit rate,
Yeah.
it's actually using less frames to frame.
Sort of. It's just being updated with iPictures, right?
Yes.
Yeah. I mean, I think you were getting there. So we haven't got very many bits, and there's all this motion here. So for the P's and B's, that's using up all the bits,
So
and
it's using
that's only being updated when we have iPictures. So that's why. Well, we've got motion compensation, so it's effectively describing the motion, but we're not sending any prediction errors, right? Until we get to an iPicture where we update the whole thing. So that's why it all changes. So 2 megabits per second, 720p effectively, is a little bit challenging. It's starting to show some problems. So let's keep going down in bitrate. Same sequence, same resolution. Sorry?
I can see the rings more.
The ring, this,
Frame is getting blurred.
yeah, it's getting all blurry, right? So we're throwing away more transform coefficients, and if you have a look at the train, it's getting blurry as we move through. What else can we see? If you look at the donkeys up the top, you get this clear view of what's happening with those eye pictures. That's snap, snap, snap as their picture is updated. I didn't have a look at the calendar then, but nothing very exciting. Anyway, so let's ignore the fact that we're struggling a bit, and let's just keep on going down to a lower bit rate, half a megabit per second, but still maintaining that full resolution. Right? And you can see that we are struggling even more.
The calendar was distorted at the start.
Yeah. The numbers are distorted. We've got blurriness everywhere. The ball is a bit of a mess. And particularly when we have this complex motion with this thing over here. What do you think's happening down the left-hand side of the picture? just I'm using this as an opportunity to just review our knowledge of encoding. What do you think's happening on that left-hand side? Why is the left-hand side worse than the rest? Oops, sorry. You see what I'm talking about? All up and down here?
You can't predict it from the
Yeah, exactly. That's right. So all of this stuff is we've got motion vectors fixing it or representing it. It might be a bit blurry. We might not be sending any prediction error, but we can't predict here, and so the representation is even worse up and down this left side, where we're forced to encode the blocks intra, and we haven't got very many bits, so it's all really blurring. Okay, we're going to ignore the fact that this is struggling so much. We're going to keep on going down. So this is 200 kilobits per second, still trying to keep that full resolution, and you see just how much the whole thing is struggling. So clearly, if we really wanted to send this at 200 kilobits per second, we shouldn't be using full 720 resolution, right? So if we go down to CIF resolution, halving the resolution at 500 kilobits per second, then the whole thing's a bit less blurry, but sorry, a bit less clear, because we're talking about a lower resolution overall, but we're able to handle the motion a little bit better. And you know, you can still see that what this ball is. And we'll go down one more step. So CIF resolution 200 kilobits per second, and yeah, it's not a great picture, but maybe it's better than this one. Yeah. Okay. So I've used you know, an extreme stress on the sorry, just a sec. Sorry, I used extreme stress on the encoding to show you the what we're talking about, to illustrate the point. But this is exactly what Netflix or anyone else who's encoding for delivery of video, a range of qualities, needs to struggle with. Right, the adaptive bit stream needs to have a number of versions at different rates or different qualities. And it's called a bitrate ladder because of you know, stepping up in quality. And each operating point, so we decide to operate at an average 700 kilobits per second or 1.5 megabits per second or whatever, requires some decision about resolution, which one's the best to use. And what resolution we should use at what particular rate is a difficult problem. Over there on the right, it's a Netflix plot, where they're illustrating the quality. Just sort of accept that that's a quality scale on the left-hand side. It's actually a scaled PSNR measure, but let's just think of it as increasing quality as we go up. And you see that, for instance, in the case of A and B, as we increase the bit rate, we're sort of saturating in the quality at different points. So if we wanted to keep going up in bit rate here, we'd be better off switching up to the higher resolution than staying here. And the comparison of C and D tells us that we can get a higher quality at a lower resolution. right? So D has a higher quality than C, but it's actually a lower resolution. Make sense? Yeah? And this also is different for different videos. So there's a plot here of 100 different titles, 100 different movies, and they're all 1080p, but the quality measure versus bitrate is all completely different. So it's hard to decide on, beforehand, which is the optimal point to encode this video, which is the optimal point to encode any video because they behave so differently. So to make things a little bit more complicated, some devices are resolution limited, as I mentioned. So, for instance, if I can decide, if I'll just get this going, I can decide, for instance, okay, if I'm operating at this bit rate, I'm better off operating at that point than there on the lower resolution. But there'll be a number of devices out there that are only capable of 720p. So I need both, right? So we need additional higher quality points for those particular devices. So life's pretty complicated, and as a result, to try to get the best out of this decision making, Netflix has moved to what they call per title encode optimization, which is another way of just saying adapting to the particular characteristics of each video. So early on, they had this bitrate ladder where for a given bitrate, they just said, okay, we'll always use 1280 by 720 at the 3 megabit per second point. But now they've moved on to making that decision on each individual title. So they perform some trial encodings at a limited set of resolutions, effectively plot what we've just seen, bitrate against quality, interpolate in between the points they have, and then decide finally to encode at a given resolution for a given bitrate. Yeah? Another interesting aspect of the encoding from that Netflix has done is to align their iPictures with shot boundaries. So shot boundaries is the change of scene, right? The graphic there is showing how they've analysed the video and decided that there's a scene change at this particular point. So all in between here is the same scene. It might involve a bit of motion, but it's the same scene. But then there's a scene cut to go to this shot and then this one and so on. And so rather than just put iPictures at regular half-second or 1 second or 2 second intervals all the way through, they're aligning them with the shot boundaries. Why? Because, they want to save bitrate, and you can't predict across the shot boundary anyway, right? So when there's a scene change here, you've got to have an iPicture. Also, when you want to jump to a different part of the video, you can't remember what happened in the last scene, you're going to want to start at the start of that shot anyway, right? So if we just organise so that an iPicture is at the start of each of those shots, that probably saves encoding. It also means there aren't those sudden quality changes due to when the iPicture comes along. It was a bit extreme in the example I showed, but you saw that we had sort of every half a second or so the picture would all change, and we avoid that if we just put the iPictures where there are significant changes. So that provides them with savings compared with encoding unnecessary iPictures. Then there's a question of what they do in chunking these up or grouping these for chunks for the adaptive streaming. And if they just did one chunk per slot, they're different variable size chunks, that's okay, they can handle that. But the chunks end up being quite small. So there are large overheads with messaging because I've got to, the client has to request more chunks. So they have grouped them together. So this is where all the eye pictures are, where the shot boundaries are. If they put one shot in one chunk, then they'd end up with all these quite small chunks. And so they collate them together and just, these are the boundaries of the adaptive streaming chunks, and they include multiple shots, but they just always start on an eye picture, on a shot boundary. Okay, so saving bits is obviously important to them because of the massive amount of bits that they need to distribute, and they distribute via their CDN, and the CDN requires storage, and of course the lower the bit rate, the more likely their customers are going to have a good experience, at least in terms of the streaming experience. They don't want to compress too much, of course, because they don't want to distort it. So they do their encoding in using cloud computing, as I mentioned earlier, and they do it in chunks. So they chunk up the, or analyse the video, decide what the chunks are going to be, and pass them off to be encoded in parallel. They're encoded independently and in parallel. So that allows them to very quickly encode, because they all of these segments of the video are being encoded at multiple rates, multiple resolutions, but they're all being done in parallel. And so that means that instead of taking maybe several days to encode a 1080p movie in all those different file formats on a single machine, they can do it in about 30 minutes by doing it in parallel. And they do it in parallel in using cloud computing, which we'll talk about in a minute. Netflix currently uses VP9, which is the old, which is the Google open source format, H.264 and H.265, which we're well familiar with, and they have an eye on AV1. Netflix is a member of that consortium that developed that new AV1. For mobile applications, and I mentioned that mobile is more important for developing countries, then they make this trade-off between random access points and coding efficiency. So if they have fewer eye pictures, it means that there are fewer points at which you can jump within the video, but it means that we save bits overall because we have more B pictures and fewer eye pictures. Are eye pictures important for error resilience in this case, do you think? Yes? In adaptive streaming, how does adaptive streaming, what transport protocol does adaptive streaming use? Do you remember? Adaptive streaming relies on HTTP, TCP, which is a reliable protocol. So unless there are massive packet losses, we should be able to rely on TCP's protocols to ensure that we don't actually lose packets anyway. We don't have bit errors. And so the eye pictures are really there to encode where we can't predict at the shot boundaries, or where we want our random access. So we have the flexibility in this case to have as many eye pictures as we want. We're not trying to erase errors, that's what I'm saying. Okay, we mentioned fingerprinting as a way of characterizing content, and this is an example of where it's used for validation of their process, because they have this automated process that will ingest a movie, decide on those shot boundaries, chunk it up into lots of different pieces, send them off for encoding, bring them back, put them all back together, and they need some method of making sure that it all has worked properly. And we can't pay people to sit down and watch the movie, so we want to do it automatically. And they do that using a fingerprinting technique. So they first ingest the content. They do an automated inspection to make sure all the there's no inconsistencies of parameters, the resolutions match what the file says, all that sort of stuff. They determine what those chunk boundaries are, and they extract fingerprints to identify or as an identifier of the particular content, or something characterises that particular content. Now they're not doing that so that they can later prove that someone's stolen it, but rather they just want to be able to check that the same fingerprint emerges after the encoding. So they do the parallel encoding, they validate each chunk, and they put everything back together in this video assembler, and then validate the consolidation, the concatenation, to make sure that no segments are out of order or none are missing or whatever. Okay. So CDNs are obviously important for Netflix, and in fact they also rely on cloud computing from Amazon. So any generic computing, so the encoding, anything that isn't involved in actually delivering the content, Netflix actually relies on Amazon Web Services for. So they use this cloud computing platform. So the application interface, the thing that you talk to when you want to go through the catalogue, any transcoding that is done is all done on Amazon Web Services. And it's just, put simply, it's everything that happens before you press play is done on the cloud computing platform. And as you're playing, it's the thing that gathers the data about what the playback experience was like. But the content itself, Netflix needs to deliver on such a massive scale, and it's so central to their business that they run their own CDN. It's called Open Connect. So after you push play, then it's the Netflix CDN that delivers the content. So there's no customer data, no discovery algorithms, anything like that. It's all just the movie and TV series content. There are about 1,000 CDN servers or locations globally, and most of them are inside ISPs for the reasons that we talked about. It's to the ISP's advantage to be able to serve directly rather than have to pay for the long distance links that would be required. So in operating their CDN, they do what's called proactive caching. So they don't rely completely on caching. So it's when this movie, Daredevil in their illustration here, when that becomes available, it's not that they just wait for someone to request it and then only then do they bring a copy across, but rather they anticipate certain titles will be needed, and they're preloaded. So they have prediction algorithms which they rely on to tell them where to put certain language files and what versions are required. And they pre-precision the content, so one copy is sent across from the origin server to Australia, and then within or between the Australian servers, the CDN would make multiple copies available, and all of that's done at off-peak times, right? Because all of this is taking server resources, and they don't want to take up those server resources at the same time that everyone's watching Game of Thrones or something. Okay. So the interconnections, or where those CDN servers are, is located at these internet exchange points, where the ISPs connect in, or indeed inside the ISP, as I mentioned before. I was going to click on that just to show you that, but I haven't got a network connection at the moment, so I might do that. Might set that up in the break. Sorry, I forgot. It's just allows you to see. It's interesting just to see who is connected into these particular peering points. So, as I said, these CDN servers, Netflix's Open Connect CDN servers, are either in these peering points or sometimes in the ISP themselves. So this is the playback process, illustrating the where the cloud computing has a role. So the cloud computing is constantly monitoring the health and the status of the Open Connect appliance, the OCA, CDN servers, so that it not only knows which ones are working properly and where there are faults, but also which ones are busy, right? And it knows which content is on which server, of course. And so that data is used to drive this steering service. So the steering service is the one that generates the URL. So when a customer back here says they want to play a particular piece of content, then the appropriate URL is sent to them so that they get the content served from the server that they want them to get it from. I mentioned about the popularity of content, that it always is uneven, in the sense that certain content is always significantly more popular than the long tail, as this is called. So if we look at bytes streamed against the popularity of the content, of course the latest blockbuster, the Game of Thrones or the latest Avengers movie or something, is being streamed by most users, and but then there's the back catalogue, the less popular movies that would account for a much smaller percentage of the streaming. So of course where you put the content depends on that popularity, and so the most popular content would just be kept in memory, in electronic memory, in these servers. Then we have the solid state drive, and finally hard disk drives are still used for this less popular content. And a single server might have this mix of technologies. So a cluster of servers, so this might sit in one of those peering centers, or it might sit inside an ISP like Telstra. Might have a number of different or multiple server devices included. And so, they have two main types. The SSD one, as you see the figures, 18 terabytes of storage, and able to stream about 100 gigabits per second, because you can pull it out of memory very fast, of course. And this is for the most popular content. And then there are what are called storage servers, which is the hard disk drive ones. Much more storage, but a lower overall streaming rate. And there are different levels in their hierarchy. So the larger clusters, or for larger ISPs, get this mix of servers, and for the smaller, lower demand, they just use the hard disk drive ones, because of course they're much less expensive. And as titles become less popular or more popular, they're moved around between these systems. So if something gets a bit tired, people stop watching it, they're moved on from that Avengers movie, they're waiting for the new one, then it becomes less popular, and it's moved from being stored in memory all the time to being served out of the solid state drive to being served out of the hard disk drive. These are the quality of experience. QoE is quality of experience. There are some subtleties about whether you decide to call it quality of service or quality of experience, but anyway, these are their measures. So they're monitoring how long it takes, how long the delay is before play starts, how often the playout device has to pause and rebuffer. You know, Adaptive streaming is supposed to try to avoid that completely, but it may not. It still may occur, and they want to know how often that happens. If there are playback errors that occur for some reason, when the user aborts viewing, they want to know. The average bit rate that's actually delivered throughout the playback. So that's, they don't, you don't know that from the files because you've made all these files available, and the adaptive streaming chooses which one to use during each time interval. And so they would want to know what the average bit rate is that you actually consumed. And they also have developed their own measure of perceptual video quality. So rather than something simple like SNR, they have developed a different way of using an algorithmic approximation to what is perceived by a human viewer as high or low video quality. But we won't. We're not going to go through into the details of that. But they use that on their scales as they measure quality and make those various decisions. And finally, I wanted to just say a word about imaging, because there are some interesting problems that emerge there that you might not think about on first considering Netflix's operations. So images are used, of course, in their interfaces to have a graphic there to show you what the movies and TV shows are all about. And so managing and processing all of those images is a significant task in itself. So they had, in 2016, they had 2 million images that they needed to process, and they couldn't afford, obviously, to manually edit and change the format for different devices and decide what where the focus of the image is and all that sort of stuff. So that leads to the requirement for automated image metadata extraction. So if there is a particular image that was originally obtained from the content owner, then for a sort of portrait style device they would want to pull out this much, and maybe for a mobile device they just want the face. In this larger image they want to be able to automatically find the figure of the human, rather than, they don't want to show that, just the sun or a piece of mountain. So they need the automated systems that can detect humans and detect faces, and where there are no humans there, they need to decide where is the region of interest. So where are most things happening, and in this case it's correctly decided, as the example that the Netflix provided, but anyway, correctly decided that this is the most important figure part of the image to show if you can only show something of that form factor. They also need to detect text, so they don't overlay their own text on top of other text. Right? So here we have, I don't know, a person of interest, I think it says, and if you made the mistake, you'd overlay on the top of that new episodes or something like that. So you'd want to be able to detect text and put your own text somewhere else. So just interesting, I thought, to see the issues that emerge when trying to automate this sort of processing. Okay.
Netflix transmit multiple versions of the same file, or?
Well, yeah, of the image file, you mean, or the video?
File.
Well, it's all driven by the adaptive streaming, so it's under client control, but there are a large range of different files available. So, so in the manifest that's available to the client devices, it includes all of these options. So it's listed in the manifest, and then the client decides for each time interval, do I request these, and there will be multiple qualities, as we've already said, for each of these. At different bit rates. So for each time interval, it's the client that decides, I'll grab this one, and then that got through okay, I've got plenty of room in my buffer, There weren't excessive communication delays, so I'll ask for this one in the next time interval, and so on. So it would.
Scalable coding.
They don't, as far as I'm aware, they don't do scalable coding, but they, I'm sure they have people looking at it, but they just have these multiple different encoded versions in all those different formats. Of course, scalable coding doesn't solve this problem anyway, but within a given format, you might be able to use scalable. In fact, scalable, scalable can help you across here too, perhaps. Okay. Right. So that's all I wanted to say about Netflix. I thought it might be interesting just to pull together some of those things that we talked about earlier. So we've been going about an hour. I'll give you the choice. Do you want to break now or a little bit later? Later? Any other view? Later. Okay. Right. Half an hour? Next topic, again, my intention is every now and again we'll pull out some new technical issue, but the main aim here is to see how some of those tools that we talked about in the early lectures come together and actually make a real digital media service work. And so the focus here is on home entertainment and specifically, mostly, digital TV. So there are quite different issues that arise in a broadcast digital TV service compared with delivery over the internet, particularly in the case where it's adaptive streaming and the client is pulling the media. So we'll start off by talking about what's involved in digital TV broadcasting and how the digital media are transported, and we'll introduce another standards body, which is DVB, Digital Video Broadcasting. It's actually a European initiative. There is, shouldn't say, I was going to say there are only two solutions, but that's, I'm not sure if that's necessarily true. There are two main solutions. I must admit I'm not sure what's used in countries such as China. They may have their own. But DVB came out of Europe. It's certainly used throughout Europe, and it's used here. But there's a corresponding set of standards from North America, from what's called ATSC, the Advanced Television Systems Committee. But when you look at the details, they're different, but at a higher level, they solve the same problems. And they're both using MPEG video, both using the same sort of audio standards. It's just the subtle details about how they're put together. So DVB is a fine illustration of the issues. So let's think about this task of doing television broadcasting. We know about encoding the sources up there, and we're going to have delivery over a range of different media at the physical layer, broadcasting. So what we're interested in is what is needed in the middle to bring things together. And we go back to our MPEG standards, again, interestingly, to the MPEG-2 systems layer. So if you recall when I was telling you about MPEG standardization, there was one group within MPEG that did the video standards, one group that did the audio standards, and another important group that did what's called systems. This doesn't sound very sexy, but that's concerned with how you pack the different streams together and how you multiplex them, how you label what's in which stream is which, how you deal with the clock extraction and stuff like that. And interestingly, although MPEG audio has pretty much been replaced by AAC and Dolby, and MPEG-2 video has been largely replaced, or is being replaced by H.264, H.265. MPEG-2 systems is surviving because it's not being replaced by a newer technology. Having faster processors and more memory doesn't help. And it's proved to be a solid solution for packaging up data and delivering it, so it's being used with these more recent standards of video and audio as well. But we need to think about what needs to be included in this transport stream, and also what other data we need to send along with our video and audio. So what information is needed? First of all, we need to understand what the transmission formats are, and the physical layer stuff, what are the frequencies, what modulation is used, all that sort of thing. And we need to know what the media formats are. We'll see that the media is carried in what are called elementary streams. So don't worry about the definition of that yet. We'll get to it soon enough. But it's basically a way of packaging up the video and audio. But we need to know which of those streams are video and which of them are audio and what format they're encoded in, but also what constitutes a program. So if we've got a TV program, we're broadcasting a TV program, we need to know which audio track belongs with which video, obviously. Otherwise there's going to be confusion. We need to know what's in the program, so metadata about the program allows us to present an electronic program guide. And we need to allow the receiver to find other transmitted programs and what programs are coming up later. So again, electronic program guide stuff. And if the TV system is a pay system, such as the cable TV, paid cable TV system, subscription TV system, then we will almost certainly encrypt the content, and we need to have some way of managing the decryption. So we'll talk about that as well. So DVB was this a European initiative. This map might be a little bit old, but you can see that all the blue bits essentially are DVB, use DVB-T, DVB-T for terrestrial. ATSC is the North American one that I was talking about, but we have some others here as well in different regions. But as I said, though the details differ, the basic approach of these different systems is the same. So DVB specifies the transmission formats, so that's not MPEG's responsibility, of course, to say, these are the voltage levels on the cable and these are the frequency ranges, all that sort of stuff. MPEG is very generic. So DVB came along and said, okay, we're going to use your MPEG specifications for audio and video, and we're going to use your MPEG-2 system specification, but obviously we need more specs, and so we're defining all these physical layer stuff. And there are different specifications for cable, DVB-C, for satellite, DVB-S, and at least here, the important one is DVB-T, T for terrestrial. Yeah. So the broadcast, the TV transmitters on the top of Mount Dandenong here transmit in the DVB-T format. DVB-C is used on the Foxtel cable for cable TV. So the formats need to be specified, of course, of the different media. We need to know what additional data we need to send and how to put it all together. So we're going to divert for a few minutes, to talk about this MPEG-2 systems layer. And there are actually two different solutions. Although MPEG has always tried to be generic, they found that they couldn't sensibly define a way of carrying or packaging together the audio and video programs for something like a TV system or a DVD or other applications with just one specification, because of the very different types of environments. And in particular, it depends on whether an error is a very unlikely event, such as if you were storing your program on a hard disk, or it's relatively common. So that would be the case where we have radio transmissions, for instance. So they did two different specifications, and they're called the program stream and the transport stream, respectively. And we'll look at each of them. Okay. So in terms of the flow of these different stream creations, there's an intermediate stage which is common, which is this elementary stream that I mentioned before, or packetized elementary stream. So if we start with compressed audio and compressed video and some other data, then we create these PES packets, packetized elementary stream packets, and then they are defined as being carried in a program stream or a transport stream. So we'll start by looking at the program stream. It's the simpler one. That's the one where the error rate is considered to be very low. So let's look at the packetized elementary stream. It's very intuitively obvious, really. There's nothing very surprising here at all. If we start with the uncompressed digital video stream, using video as an example, then each picture, which, because it's uncompressed, has the same size, in this example 830 kilobytes, they're called presentation units. Just for the terminology, you don't have to memorize these things. But after compression, of course, they involve different picture sizes. Some illustrated examples are there. They're called access units. Again, don't bother memorizing this stuff. And an elementary stream is nothing more than the concatenation of these access units together in one stream. But every now and again, we will put a header, and this is what makes it a packetized elementary stream. Right? So what goes in this header? We have a PES packet header, PES packet payload. The characteristics of these PES packets are that there are very few restrictions on what you can do. It depends on the designer. So they can be variable length. They could contain one access unit, so one picture, for instance, or they could contain many. And they needn't even start at the start of an access unit. So we could, here, this is an access unit, a large frame, an iPicture, say, and we've got a PES packet starting in the middle here. So we don't have to start on the boundary, because we're going to assume that, sorry, I'll come back to that. And the system designer can decide whether they're fixed length or variable length, whether they have a fixed or variable number of access units inside, and whether you start on an access unit boundary. The PES packet header includes lots of fields that we're not going to worry about. I'll just highlight a couple. So not surprisingly, there's a packet start code, so we can easily identify where the start of a PES packet is. There's an ID to identify which this stream is, something about the packet length, so we can get the framing right to figure out where the next packet starts. We have timestamps. Remember the timestamps? Tell me what a timestamp does. What do we... Exactly, yeah. And why do we have the two? When to decode and when to display?
One is for decoding sequence, one is for display.
Sorry, what was that?
One is for decoding. It tells the decoder when you decode the,
Yeah.
and one is to display.
It's for audio and one for
No.
Not in the same order.
Yeah. IPV and
It's the existence of B pictures that demands this, right? We need to decode some frames before we display them, because we need them for further prediction. So I dealt with all that. And anyway, the timestamps are important. We recognise that we need those timestamps so that we can synchronise exactly when to play this the part of video that's in this particular PES packet, or the piece of the audio. So how do we generate a program stream? So remember, if I've already confused you with the terminology, if we've got these PES packets, how do we generate one of these program streams? We multiplex. It's very simple. The program stream is just a free combination of the video, the audio, the other data packets. We don't have to keep only video within a program stream. We just multiplex them all together in whatever way we like. But we do create these packs, as the just as a different name to packet to identify what we're talking about. Again, don't memorise what a pack is, it's not worth it. Just want you to understand what a program stream is. So we have a pack header at the start of every one of these collections of video and audio and data pairs packets. And sometimes we have an additional header, a system header. We're not going to go through the details of what's in each, but we'll talk about some of the main characteristics. And essentially, we have this pack header for things that we need to know often, and we have the system header for things that we need to know less often, so things that don't change so much. So, for example, the pack header has the system clock reference. So this is remember that's the last one, what we were talking about before were timestamps. They tell you when to decode and display. The system clock reference is the periodic indication of what the clock is right now to allow synchronization of the decoder time, decoder clock. It's also telling us what the mux rate, the multiplex rate is in the pack, so you can make sure that you can handle it at the decoder. The system header is the one that is less often, in green in my code there. And so this is things that are not going to change so often. So things like the number of video and audio streams in that, or the number of video and audio elementary streams in the pack, or how the clock rates are related to one another, how the audio clock rate is related to the video picture rate. This sort of thing is not going to change very often, but we need to make sure it is communicated. So a pack contains any number of pairs packets in any order, right? With few restrictions, except that a packet header has to be there at least every 0.7 seconds. And the reason for that should be a pack header, sorry. The reason for that is we need to make sure that our clock reference is maintained, our clock synchronization is maintained. So the characteristics of this program stream, so a program stream being a series of these packs, each containing the pairs packets, is that we have long variable length packets, and so the effect of errors is going to be pretty significant, right? If we lose the pack header, then we don't know where the start of it is. We might take some considerable time to find it, so we might lose quite a lot of data. So the entire pack is likely to be lost. That could be many kilobytes of data, could be multiple video pictures, for instance. The variable length requires a packet start identifier, so we need to be able to identify this. We also have, I think we also had some other framing information about what length it is, but an error in this identifier could mean loss of synchronization, as I mentioned. So, and it's for that reason that these program streams are fine and they're very efficient, but they're really only suited to error-free environments, and that's why. And the reading from a local disk drive is an example. So an error at the disk level, it's not that we're bit error free, but there's so much error coding on top of a disk that by the time we read off it, the bit error rate is very low indeed. And there's the application, right? We actually use this program stream in DVDs and presumably Blu-rays. I haven't checked, but I'm pretty sure it would be the same. Okay, so that's not really used for transmission though, and we're mainly interested in delivering over networks, and in this lecture we're talking about delivering broadcast TV streams. So we are interested in following down this other path to this transport stream. So let's see how transport streams are put together. In contrast to the program stream, the transport stream is very rigidly defined. So instead of having the freedom to make them as big as you like, containing anything, but rather they are a fixed length. There are 188 bytes, including a 4-byte header, and if we have a new pairs packet, that becomes the first byte of a transport packet. So we don't. You see here, we haven't allowed that this last, sorry, right, when this pairs packet finished, we could have filled up. This is drawn slightly strangely, but that's empty. It's around the wrong way, but anyway. We could have filled this up with the first part of this, the next pairs packet, but that's forbidden by transport stream rules. And so when we finish a pairs packet, then we finish then we just stuff the remaining 188 bytes and start the new pairs packet in a new transport packet. What else?
So the transport packet has 188 bytes?
Yes. Yeah. The reason for that, I'm pretty sure, if I can, is that it was defined back in the times of ATM. If you're familiar with ATM cells, no. I don't want to get too distracted, but essentially.
So the size of TS is 188.
Yeah.
It has a couple of elementary stream, might have a couple of...
I'll talk about that in just a second. But it's really not terribly important. But back in the sort of early 90s, when the internet was emerging, the computer industry was developing their protocols to support all of their communication between computers. At the same time, the telecommunications industry, they were essentially in competition with one another. The telecommunications industry was saying, don't worry about it, guys, we'll provide all the telecommunications you need, and they were developing a high-speed digital multi-service network which was going to be based on cells, which are fixed-length packets. They were going to be 48 bytes, 48 bytes of payload, each one. And of course, if you've got a fixed-length packet, you can switch it a lot faster. But as opposed to an IP packet, which has variable length, which makes things a little bit more complicated. Anyway, who won is pretty obvious, right? We're now in TCP/IP land, and these cells are not used in telecommunications networks. Interestingly, they are still used inside routers, inside switches. So variable length packets go into the switch, they're chopped up into fixed length cells, they're switched super fast, and then they're put back together. So anyway, so that's just a little bit of history to explain where this number comes from. If it fits conveniently in, what is it, 4 48-byte packets with, I don't know, with some overheads, something like that. Anyway, whatever the history, we have these 188-byte packets. And in answer to your question, the transport packet contains data from only one pairs packet. So what's inside here can only be video or can only be audio. It can't have a mix, right? Because they always come from one pairs packet.
So only one elementary stream packet, or might have more, or only one?
Well, there'd be other pairs packets for, say, the audio stream, but they would also be contained in their own separate transport packets. Never have a transport packet with video and audio together in the same one. Yeah?
But I mean, it had only one video. I cannot have two videos.
No. Another video would have another pairs packet stream and another set of transport packets. Okay, so as a result of this, there will be some bits wasted to fill the last transport packet, as sort of shown here. But we can minimise that wastage if we want by simply making these pairs packets longer. Right? That means that a smaller proportion of transport packets will involve the end bit, right, if we make them longer. So once we have these transport packets, what's called a transport stream is simply a free mix of those transport packets. So putting them in these rigidly defined transport packets is what's important, and then you can just combine them in or put multiple packets out in whatever order you like. So what's inside this transport packet header? It's only a short header. It's only got 4 bytes. There's a sync byte, the first the first byte, not surprisingly, just to ensure that we, when we expect to have a new transport packet, we do indeed have one. There's some other stuff that we're not going to worry too much about, things like allowing for the possibility of different priority, scrambling information, continuity count if we're counting data that passes that involves multiple transport packets. I'm not concerned about the details here because really the important thing is this PID, this packet identifier, because that is going to label our video stream, or a particular video stream, or a particular audio stream. Yeah, and so we'll see how that's used a little later. The program clock reference is the these are the clock references for in the MPEG case. We talked about how to do the clock synchronization using this type of feedback loop in a receiver. And the clock references are these program clock references, PCRs. And we had a graphic when we talked about it showing these PCRs for a strip of video, I remember. They're required at least every 0.1 seconds for a transport stream, and they maintain that synchronization between clocks. So the characteristics of the transport stream. We talked about the characteristics of the program stream. So now we have short fixed length packets, and they're much less susceptible to errors for obvious reasons. If we lose a synchronization in a transport packet, we know exactly how long they are, 188 bytes. We know exactly when to expect the next packet. So we should be able to synchronize very fast, and we lose relatively little information if we lose a packet. So these are suited to error-prone environments such as broadcast TV, and they are indeed used within the DVD specification for carriage of broadcast TV. Okay, so that's a change of topic. We're going to now talk about this program-specific information, which is essentially metadata. The other information around a program's broadcast TV stream that allows us to understand what's inside it and how to use it. But as promised, let's take a short break, and I'll carry on after that. In the meantime, I'll see if I can get that link going. Sorry?
This is all we are talking. It is about broadcasting channels.
Yeah. So, broadcast TV channels.
channels.
Yeah, TV channels. So this is what I was trying to show you earlier, which is just that there's this database, a peering database that gives you information about each of the peering points on the internet, which is kind of interesting. You have to rummage around just to understand what's happening with the networking. So this particular peering point seems to be run by an organisation called Megaport, but it shows all the connections that are into this peering point. This is the peering point in Melbourne, and you see ARNet there, so the Australian Academic Research Network, which is all the universities, have a 10 gig connection into this point. Akamai, remember we talked about CDNs and Akamai being one of the major providers, so they've got a link into it. You can search down here and find all sorts of organisations that are linked in at this particular point, but amongst them is there we go, Netflix. Netflix servers are connected in at this particular point, 20 gig interfaces, and all the IP address stuff is there as well. And various telecommunications providers will interconnect to one another via one of these peering points. Anyway, if you're interested, the URL is there. You can rummage around and go to some other ones and investigate if you're interested. Trying to do two things at once. Let's move on to what we were talking about before, which is the metadata that's associated with broadcast TV. And what metadata is needed, and how it's provided. So metadata in the TV or DVB language is called program-specific information. And we need to use this metadata to sort out which, all those video and audio streams, subtitling streams and so on, and to find out which ones are which and how they're put together. And so that raises a question about what is specified by DVB and what's specified by MPEG if we're using this MPEG-2 systems layer. And as a general guide, MPEG's aim was to try to be generic. So things like which video is with which audio is the sort of thing that you would expect to be used in very many applications, and so that was specified by MPEG-2. If it's specific to TV broadcasting, so things like the electronic program guide, then that's not generic, and so MPEG left that to other bodies and DVB came along and filled that in. Does that make sense? I'm sure there are going to be some grey areas, but that's as a general guide that makes sense. So if we go back to that transport packet, I emphasise the importance of this packet ID as identifying a stream, and that's what we actually rely on. And we use those packet IDs in a number of different tables. I'll tell you again, don't bother thinking that you need to memorise the names of these tables. It can be pretty confusing. I'm already presenting 4 different but similarly sounding tables to you. But the point is that we can use these tables or build up the information we need from these tables, and I just want to go through the process and illustrate that. So what information is provided in these tables? Some of it is generic, defined by MPEG-2, and some of it is specific to TV broadcasting, and we'll come back to that, what DVB provided. So what are these? So let's go through these tables. So there's the program association table, which tells us which programs are available in the transport stream. So when we, at the front end of a TV set, where we have the RF interface and we demodulate and extract our bit stream, then we've got a set of TV programs, right? We've got more than one TV program. To divert for a moment to talk about the physical layer in the Australian standard for television broadcasting, there are 7 megahertz channels in the spectrum, each one used by one of the TV multiplexes. and depending on how much bit error correction they put on, and it's up to the broadcasters how much they use, there are around 20 or 22 megabits per second available within that 7 megahertz channel. And each broadcaster can use that 20 megabits per second to put in as many TV programs as they want. Some might be HD, some might be standard definition, and depending on their bitrate requirements, you could have more or fewer TV programs at the same time. So the point is that there are going to be more than one video and audio in one of those 20 megabits per second streams. So we need to figure out what they are. So the program association table tells you what's in there. The program map table tells you what are the identifiers of the elementary streams that make up a particular program. So if I'm interested in watching ABC News channel, then I need to know which is the PID for the video and which is the PID for the audio for that. And then there's other information in these tables which are less important, but we'll talk about them, which can provide information about how we can find other programs outside our current multiplex, or the conditional access information if the data is scrambled. So graphically what these tables show us is as illustrated here. So as I said, there are 7 megahertz channels that are broadcast. We might have 20 to 22 megabits per second digital in a transport stream, and our this program association table tells us which programs are associated with this multiplex. So so it identifies what these programs are, and then we need to be able to figure out which video stream and which audio stream and which captioning is associated with program number 3 and which with program number 2 and so on.
We might have multiple programs in each transport packet. We might have multiple programs in each transport.
In each transport stream, yes. The transport stream, not within one transport packet, because remember, one transport packet contains only video or only audio from one source. So, but this transport stream will include multiple transport packets from multiple video sources.
That's half as a multiplexer.
They'll be separated in this stage. Yeah, I'll check with you in a minute to make sure it makes sense. So the network information table, if it's used, it isn't always used, can tell you what other transport streams are available on some of these other channels. So the way the things tend to work here anyway, I'm not sure if it's very different in broadcast TV elsewhere, is that when you get a television set or a new television set, or you bring one from interstate or something, then you have to have it search through the spectrum to try to find channels. But there's the provision here to allow for information that tells you if you're associated with this, if you're decoding this spectrum, this channel, this analog channel, what are the other channels that are available to you and what's in them? So that can be carried, but as I say, it's not used, as far as I know, on our DVB-T network. And then there's the conditional access table, which manages keys and so on if the data is scrambled, and we'll talk about that a little later, probably tonight or maybe not. Okay, so in terms of the contents of these tables that allow us to do that, let's just look inside one of them. An obvious question is how you start, right? You've got a TV that you just got out of the box. It doesn't know anything about the transport stream that's being broadcast to you. It doesn't know anything about PIDs. So how do you actually start? And if I gave you a few minutes to think about it, you'd think, well, maybe there's some reserved PID, and indeed there is. So in fact, we look for PID 0. Right? So there's a continuous stream of these transport packets coming through from our decoder, and they contain lots of video and audio and subtitles and other stuff, and we're just going to ignore them if we've just turned the TV on, or if we've just unpacked it, until we see PID equals 0. When we see PID equals 0, we think, aha, we're going to have information about this program association table, and that's what's going to tell us what's inside this multiplex. So without worrying about the protocol, exact protocol, this is the data that's included, or this is examples of the sort of data that's included. So that's telling us that if we want program number 3, so maybe I haven't chosen it, program number 7, although my other examples illustrate this one, but you know, channel 7, say in Melbourne, if you're familiar with the channel 7 multiplex, then I find out about the program map table, that is the audios and videos that are connected together, by going to this other PID. Okay, and if I want the information for channel 3, or program number 3, I need to look for PID 1127, and that'll give me the program map table. Right, so if I link this back to my previous graphic, right, the program association table is telling me if I want program number 3, this data, I need to look for PID number 1127. Okay, so this allows me to start my tables. Okay, so this tells me that if I go to PID 306, I'll find the program map table for program 1. If I go to PID 1127, I'll find the program map table for program 3, and so on. Another reserved program number is used there. If it happens to be, if it's 0, it actually means it's the network information. I'm not too concerned about that. Don't worry too much about exactly how that works. The point is that there is a reserved number that allows you to find that network information table if it's present. But I want to mainly focus on how we figure out the program information.
So the number of programs here are the basically channels, number of channels that we got on the TV.
Sorry, these two columns?
Yeah.
No. This is the program number. So this would correspond to like ABC or
I mean,
9 network or
like
something.
program 3 is something like ABC, program 7 is like channel 7.
Yeah, exactly. That's right. Yeah. And so when I want to find out more about what's in each of those programs, I go to this other PID. I think it'll make more sense when we show this one. So I've seen that if I want program number 3, I should find the details of what's inside by going to PID 1127, and this generates another map. And this is the one that gets down to the video and audio level. So this is saying if I want to watch program number 3, then I can if I just look for PID number 726, this gives me all the video packets. And if I want the audio in English, they're in PID number 57. So I just pull out, whenever I see a PID equals 57, I pull out those packets and send them off to the audio decoder.
So all video or one packet? All video packets
Just,
have this number, PID number.
This is for one program, for one television program.
Yeah,
Right.
but one television program
Yeah.
has multiple video chunks.
No, just one stream of transport packets. Yeah. We're also seeing where we can find our program clock reference. Right? That's included in one of the other streams, and in this case, we're seeing that it's included in the video packets. So when we pull off we should search within the video transport packets, and we will find the program clock reference included there. Okay, so the network information table is the one that I mentioned is available to provide further information about channel frequencies and satellite transponders, modulation characteristics, all that sort of stuff. But that's very specific to a particular application. So what MPEG did is they defined the existence of this network information table, but they didn't populate it. They effectively allowed it allowed others to use it as they needed. And regarding this conditional access one, conditional access is another way of saying scrambled. There's another reserved PID that allows you to find out information about the scrambling system and keys and things. But again, the details of that would be application specific. So MPEG defined the existence of the table but didn't fill it in. So maybe this next graphic will help to illustrate how that that use of the PID works for that same example of the program number 3 and how we pull out from the multiplex what we want. So here we've pressed program number 3, or when we turn our TV on, we're still, you know, the last time we were using it, we were in program number 3, and we had selected English, or the default was English, or whatever. And within the processing stage, looking at the transport, this transport layer, or the MPEG-2 systems layer, we've got a PID filter. Obviously, this is a key function, right? We're going to be searching all of these incoming transport packets, and depending on the PID, we will either ignore them or we'll send them off to our decoder. So the first thing that's going to happen is we're going to find that PID equals 0. Right? Remember, that's the reserved number. And if we find that reserved number 0, it's going to allow us to extract the program association table. Program association table is which video is associated with which audio. So given that we've selected program number 3, we know that we are looking for program association table that's in, the program map table. Map table? Forgotten myself. Program map table, yeah. So, so we know that we're looking for the program map table in PID number 1127. So again, our filter is going to sit there just ignoring all of these transport packets as they come in until it finds number 1127. 1127 tells it that for channel 3, for program number 3, the video is in, once we've extracted it, it's going to tell us that the video is in packets with PID 726, the audio is with packets with PID 57, and the captioning, I think, is in packets with PID 123. So our PID filter goes to work again, and it's going to look for any of these. Right? And once it finds a series of, well, somewhere in that that collection of transport packets that come as a stream, it's going to find some with a packet ID of 726, and whenever it does that, it's going to send them off to the it's going to extract the PCR, sorry, from those packets, but it's also going to send those packets off to the video decoder, right? Because this information has told it that anything with 726 at the start is video associated with program number 3. And so before I continue that, and back here, within that same multiplex, there'll be another set of PIDs that identify the video for program number 2 and program number 1. Okay, what we've looked at here is the program map table for program number 3, and so the videos are in number 726 in this example. And the filtering will continue where it finds transport packets that are labelled number 57, they go through to the audio decoder, and where it finds packets with number 123, they go through to captioning or titling or subtitles. Right. Does that make sense?
What makes scrambling is doing?
We'll get onto the scrambling in a little while. Does the process make sense anyway? Yeah? So what do I want you to take out of this? As I said, I don't want you to memorise exactly the terms program map table, program association table, but I guess I'm trying to demystify how we can get the specific video that we want associated with the specific audio we want, and I want you to take away the fact that we need some way to start off this process. So we need a default, a reserved PID that will give us some way of starting from which we can determine via these tables which are the ones that we want for our particular choice of program, and so we know which video data to send to a video decoder, which audio data to send to an audio decoder, and so on. Okay. So what we've talked about there is the data that, or the metadata really, that MPEG has specified in their systems definition. Now DVB added to that because they needed to add the bits that are specific to a digital TV service. So they filled in the network information table, they filled in the conditional access table, but they also added their own tables for other reasons that are illustrated here or described here. So for instance, there's a service description table which instead of labelling a TV program with a number, gave it a name, so you can do things like have Channel 9 Melbourne as included in the data that's sent to the receiver. They allowed the association of groups of services, so if you wanted all the sports programs to be sold in a package on a cable TV service, then you could define them in logical groups. Information for an EPG, so future events, the start time, the duration, all that sort of stuff, very TV oriented, and so that's what DVB had to add. The other stuff is fairly self-evident. Anyway, the main point is that where the program-specific information is needed for a TV service, but it's not generic, then it's the sort of thing that DVB had to add, and ATSC would have added in North America, and so on. Okay, so let's talk about conditional access while we're on a roll talking about digital TV. This provides conditional access presents an interesting problem from the cryptographic point of view, right? Because we're broadcasting, so we're broadcasting to 1 million users. Or however many. And so this is a pay TV system. It's not for the free-to-air broadcasts, but a pay TV system such as Foxtel here in Australia is broadcasting over whether satellite or cable to a large number of users, say 1 million users, and they want to encrypt the data that they send out because they want to control who receives it. They don't want people hacking in with their own set-top boxes and decoders and just getting the service for free. And they also want to make sure that people who have subscribed and have the cable brought into their premises, and maybe they already have a box that decodes it, once they stop subscribing, they need to stop access, of course. They also want to at least the way the business model seems to be managed for pay TV services, they want to sell you chunks of programs. So they don't want to just get you to subscribe and get everything. Rather, they want to sell you the movie package or the sports package or something like this. So in a sense, they want to individualise the encryption. Right? Because only specific individuals are subscribed and have paid, but on the other hand it's a broadcast signal, so we can't do an individually encrypted stream for every individual user. So, any thoughts on how you might handle that? Maybe a little hard, giving you no thinking time at all, but
And there's an encryption for everyone.
sorry? Yeah, but we can't use an individual encrypted stream for everyone, for each individual, because we're broadcasting it. So the way
We
it's...
have that card, right? It's sim like card. So we insert that in that
Yeah.
insert setup box.
Yeah.
They just activate that once we pay the.
Well, that's right. That's the physical process. We activate the personal card, but that can't have an individual encryption key just for you, because the same signal is being broadcast to everyone else. And so the way it's managed is as something of a hierarchy. They actually we encrypt the stream with a single key, but then we encrypt the key on an individual basis. So this is the way it works. We've got this at the head end, so the broadcasting end. We've got this stream of transport packets. That's what they're intended to show. And up the top there in the clear, so they're unencrypted, but then they go through this encryption stage, and so all this data is scrambled. We're not going to talk about encryption algorithms here. We've got too much stuff to talk about with regard to media. But I'm sure you understand the principles behind encryption, that you need some sort of a key to decode it. So for the simple illustration, we've got this thing called a control word, which is actually a key to this encryption. But as I said, the way around this problem that I talked about earlier is to actually encrypt that key and send an encrypted version of that key. So every now and again, there is this thing called an entitlement control message, which includes an encrypted version, and it's identified via a PID, right? So that a conditional access table will tell you information about what that PID is. So when the decoder sees that PID, it knows that it's an ECM, an entitlement control message, and it'll hopefully be able to extract what this key is, and once it's extracted the key, it can decode. So the encryption of this control word is done by another key, a service key, which is encrypted in turn by an individual key. So this here we have in a subscriber management system. So this is the customer database in Foxtel headquarters. They have a database of all these individual keys that are owned by individual subscribers. So there are literally like a million of them. And they progressively go through encrypting this service key in multiple encryptions using these different keys and broadcasting them in another set of messages, which are the entitlement management messages. So if you don't need to memorize these words, but just to try to make sense of it. So this is the controlling access, right? Because it's the actual key that does the encryption, and this is managing it, right? Because of comes from the subscriber management system. So these entitlement management messages contain encrypted versions of this service key. They're encrypted according to with individual copies, and so embedded in the broadcast data stream is a series of these things. And so when you first want one of those entitlement management messages, you just have to wait until yours comes around. So what happens at the decoder is this. We've got the encrypted data coming through, and initially, of course, we don't have the key to decrypt it, or if we haven't subscribed, of course, we don't have the key to decrypt it, and so we can't decode a video or the audio or whatever. Worth mentioning that we don't encrypt the header, of course, in the transport packet, because we could end up with random data in it. It could end up with a PID that matches something that it shouldn't. But also, the pay TV provider wants you to know what is available. It just doesn't want you to be able to see it. Or maybe you hear the audio and they scramble the video, something like that. Anyway, you've got these decryption systems sitting there in the decoder or the receiver, waiting for these entitlement messages to come along.
So every now and again there will be an entitlement management message that will contain a key that matches yours, and your keys, maybe it's changed by a smart card or some other system. This allows you to decrypt this service key, and armed with that service key we're now looking for the ECM, and when an ECM PID is identified, then we're able to decrypt this control word. We can then decrypt the stream, and we get the data back in the clear, and we can demultiplex it and decode it. Okay, so by using this kind of hierarchical representation, we have a single encrypted version of our content, but the keys themselves, or the key to that encryption itself, is encrypted, and the keys to allow that to be decrypted are individually sent to us over the broadcast channel. Okay. Where are we going for time? Okay. So, I wanted to say something about, while we're on the subject of topic of home entertainment, I wanted to say something about the connected home, which is a term that's used these days for the fact that we have lots of different media in particular going to lots of different devices within the home. Not so much broadcast TV, though there is a connection there, but more maybe with media or entertainment services over the internet. And then we will finish off, if I squeeze it in, by talking about 3D TV. Otherwise, we'll talk about that next week. So, connected home and the challenges that represents. Well, as we increasingly are bringing these different media services into the home, probably most commonly via some sort of a internet gateway, we're putting challenges on putting strain on the internal home network to try to deliver to multiple devices. So we could have multiple people in the same home trying to stream multiple simultaneous HD TV streams to different devices, so two Netflix streams, for instance. At the same time, someone might be doing other data applications, or someone might be playing games over the internal home network. So even if we can manage appropriately the network to get to the house, it can be a challenge to support all these services within the home. And without diverting too long into the physical network layer, it's worth recognising that there are a number of different home network technologies, but they're not equally capable and they're not equally applicable. So if you were building a new home today, you'd put Cat5 or Cat6 Ethernet LAN cable around, because it for devices that don't move, like your smart TV, that's a reliable way of getting information to it. But most often these days we rely on wireless, at least in this country. There are other solutions that are available, but they're not so common here and not so reliable. So, for instance, in the US, where they've had a long history of coaxial cable TV, they have, often in their homes, they have lots of points that are connected up via coax, and so that can be used to distribute data around the home. They also, in the US again, it's more common to have lots of telephone points. So they're all connected up with twisted pair cable, which is good enough to provide reasonably high rate data services. So that's available, but here it's not so common. Power line is available. You can get modems that plug into your power points, and they use the wiring for the power to deliver data services. Don't really know why they're not so common here, but I guess it's just more convenient to use to use wireless if you can. And of course, the wireless modems have increased in speed a lot increased in rate a lot lately. Nevertheless, the home network is an environment which is outside the control of the service provider or even the network provider. So usually it's self-installed by a customer, of course. They just plug in their modems wherever they want, wherever it's convenient. And it's not necessarily the ideal location because of problems of transmitting wireless through walls and through solid brick, for instance. And it's all outside the provider's control. And so, and it's also true, as I was suggesting earlier, that delivery of services from outside the home, so my Netflix service via my Big Pond ISP account or whatever, can be affected by other things inside the home because someone else is is using the PC to play games or something similar. And the support of multiple HD video streams can, despite the fact that modern wireless Wi-Fi can give tens of megabits per second throughput, that's not always the case because it depends on the particular configuration in the home, the distance from the modem and so on. And so it can be challenging to support all of these media streams. And as I mentioned, some of these home network technologies aren't well suited to the Australian home environment just because of we don't have typically lots of telephone network points or lots of coaxial cable wiring. And these other solutions are subject to interference and dependent on locations in the home. Even the power line, the power line modems, if you plug a pair of these things into your power points to provide a data connection over that wiring, can make a big difference which particular power points you use because of reflections or the quality of the terminations. The power connection to deliver 240 volt doesn't necessarily match the sort of have the sort of impedance matching and all those sorts of things that are important at higher data rates. And we've got to remember when we're thinking about home networks that those early requirements that we talked about in the first lecture, I think that for media we need this continuous high bitrate availability. And interestingly, for Wi-Fi networks, for instance, you can get good connectivity without necessarily getting high throughput. To deliver around the home, there are a number of different proprietary and standardized solutions. So a standardized solution is always an interesting one to look at because it's more, it can be widely adopted, but also it's open, and so you can read all the documents and you can find out all the protocols that are used. So DLNA, which is somewhere, sorry, haven't defined it. Digital Living Network Alliance is an industry forum that has standardized a means of connecting devices within the home. Anyone heard of DLNA? No? Okay. So the idea is that PCs and games consoles and tablets and such like, and phones, mobile phones, can be compliant with the DLNA specifications, which means that the protocols are such that they can easily exchange media, in particular, between them. So you could. So the idea is that you've got a network attached storage, a NAS box in your home. So you've got storing all your media files. And you've ripped all your DVDs and something. You've got them all on a disk. So if all your other devices, or if some other devices are compliant with DLNA, then you would be able to watch those videos on your games console or on your phone or whatever, and it would look after all the protocols to allow that to happen. That's the intention. So within DLNA, of course, they've narrowed in on the particular specifications of the different layers to allow this to happen. So there's a specification of an agreed set of media formats, but also specific resolutions, sampling rates and all that sort of stuff. There's streaming protocols to use, so is it using IP, is it using RTP? We talked about RTP. And means of discovering what other devices are on the network. So you've probably heard of UPnP, Universal Plug and Play, before. It allows you to just plug a printer on a network and everything knows that it's there. So the same protocol is used for DLNA. And it's defined these specific classes of devices. So depending on whether if your games console is a media player, it needs to have a certain capability to play out, and similarly in the other categories. So you see some familiar protocols in this set here on the right. So for instance, there's we need to be able to support JPEG and MPEG-2 and GIFs and PNGs and so on. AAC audio, H.264 video. To be able to discover the devices, there's this UPnP, the Universal Plug and Play thing that I've talked about before. The media transport could be HTTP or it could be RTP. We're carrying data over IP, version 4. That might have changed now to become more broadened to include IP version 6. And then there is the network connectivity via Bluetooth, via all the different flavors of Wi-Fi and so on. There are alternatives to DLNA. DLNA is the open standard, industry forum standard, but there are lots of alternatives, some of them proprietary, some of them open. So there are proprietary solutions like Apple's AirPlay. It does essentially the same thing, allows you to share media between devices. Sonos audio systems have their own protocol. They actually don't even use Wi-Fi. They have their own wireless format, wireless network. Someone bought Sonos recently. I don't know if anyone know. I think I got an idea. A big company bought them out. Anyway, that's an example of one of these home network media sharing protocols. And there are also some open ones, so Miracast and some of these other ones have emerged with different groups being involved. Netflix and Google were involved in this one. I'm not sure if that's how successful that one's been. Right, so I'm just checking timing. I reckon we've got time to get through 3D TV before we finish. So let's talk about 3D TV, because 3D TV throws up some interesting technical challenges and some more technology solutions, which I think are worth having a look at. So, 3D TV, it's really misnamed. It's not 3D, it's stereo, right? Because there is a difference. They provide this depth perspective for our video programs, of course. We need some mechanism with stereo imaging to be able to have two views. I mean, this is absolutely fundamental. The way we determine depth, well, that's not strictly true, sorry. Even if we close one eye, we can have some perception of depth by, if we move, we see the parallax difference in appearance, and when we focus on different depth, we get some clues about depth. But to get full stereo experience, we really need to have two views, and two views delivered to each, different view delivered to each eye. So we'll talk about how we can do that in just a moment. This is maybe a little bit misplaced, I'm sorry, but anyway. There's a wealth of material already recorded in 2D, as you're obviously aware, with all that history of conventional 2D television and 2D movies, but to convert to 3D is very hard and very expensive. It's hard to do well, anyway. And so, in general, if we want video content to be consumed in 3D, it really needs to be produced in 3D. There have been various efforts to convert 2D to 3D automatically. But even when it's done with lots of manual intervention, it can be can have all sorts of strange artifacts. But let's talk more about how we create these two views. So essentially, if we're going to have two views, if we're going to have our eyes are going to see two different things, then we need to separate those two views either at the eye or at the source of the image. I mean, there aren't very many other possibilities. So let's talk first about separating them at the eye with some form of glasses, and there are different technologies, some of which you're probably familiar with. So we can use the LCD shutter glasses. These have LCD displays, or LCD panels in the eyepieces, and they go from transparent to blocked, completely blocked, although it's not visible to us, but they are switching in synchronism with pictures on the TV. So we show the left image on the TV or the cinema screen. That's the technology is used there as well. At exactly the instant that the right eye is blocked off, and then we switch to the other one. So this obviously halves the potential frame rate from the display device, but our modern TV displays have a very high frame rate, so that's not such a big problem. Polarizing glasses are actually more common in the cinema because they're cheap, right? And the cinema operator needs to hand them out to hundreds of people, and they get them back damaged, and so they can't really afford the more expensive LCD solution. So the polarizing glasses, of course, rely on separate polarization for the two views. In the case of TV, this can be done using actually a different polarization for each scan line on the TV. So every second row of pixels can be differently polarized because of a polarizing filter on the front of the TV. It's not such a common solution. Most commonly, TVs use the LCD shutter approach. But as a result, there could be a reduction in resolution because we're only getting half the scan lines. There's this old coloured glasses approach, which was originally used in the first 3D cinema attempts back in the 1950s or so. They were originally just blue-red filters. Have you seen these before? Yeah. So the images that were projected on the cinema screen were either went through a blue filter or a red filter. These glasses separated the views again to go to the eye, and then our brains just sort of munge this together and somehow come up with a monochrome black and white image as a result. There have been more recently there have been other variants on the particular colours, and it's even possible to get some perception of colour, but generally the picture quality is poor, and no one's really considering those for 3D TV or even cinema these days. The alternative to separating our images at the eye is to separate them at the source. All right, so and this is called autostereoscopy. It means achieving this stereo vision without having the glasses. And there are two basic approaches. I'm just thinking for a second to try to remember if there are any other approaches. These are certainly the two main ones. So one is a lenticular lens, and if we look down on the top of a screen or an image that uses this lenticular lens approach, we would see, as is shown in the graphic here, we see a sort of a bubble of a lens. You've all seen these things in 3D postcards. I meant to bring one tonight just to hand it around when we're talking about it, but I forgot. And on these 3D postcards, they have these ridges, right? Remember, you've seen those? Yeah. If you run your fingernail across one of these 3D postcards, you can feel little ridges. Yeah, they're the lenses. And the fact that they are lenses, they actually have roughly this shape, means that behind the lens there are two pixels, and because of the angle and the distance that you're holding them from your eyes, the lenses focus one pixel onto one image, onto one eye, and one pixel onto the other eye. And so that's why as you turn these things, you get a different, you can get a different effect. So we've talked about it in terms of these these 3D postcards, but exactly the same approach can be used on a TV. You can have a lenticular lens on the front of the television. These can be pixels that can be on the front of an LCD display, and the different pixels are focused to the different eyes. The alternative approach is what's called a parallax barrier, and I'm sure you understand where the name comes from as we look at how it works. And the idea here is that there's a physical barrier in front of the array of pixels on the screen, again looking down on the top. This is what it's supposed to do. And just because of the geometry here, we can see that the left eye can only see the red pixels and the blue eye can only see the blue pixels, and the barrier is blocking the alternative view. And that barrier can be another LCD display. Right? We can also have narrow strips that provide this barrier. There are a couple of characteristics on these that will be common to these audio stereoscopic solutions, though. As you've probably realised either before or while I was talking, the left and right eyes need to be in just the right spot, right? Just because of this geometry. So there are what's called sweet spots, positions where the viewer gets this stereo or 3D type of experience, but if they move left or right, then the effect is lost, or they have to move to another location. You kind of, if you were doing this in the home, you'd have to put a cross on the couch at exactly the right spot to sit, or else you'd have to sit at somewhere else. And the need to accommodate these multiple views in the same screen means that we can lose resolution in some way. But they have been used particularly for 3D advertising displays, in shopping centres and stuff. And sometimes they use more than two views, so you can actually walk around a screen and get multiple views. It can look a little bit like you are actually moving around a solid object. But the more views you have, the lower resolution you have, right? So instead of having two pixels behind each lens, maybe you have four. Right? So you keep on losing resolution. Okay. Some of the problems with 3D, not just 3D TV, but also 3D in the cinema. We'll talk about digital cinema next week. Actually, it'll be one of the last systems that we look at. I don't know if you're in this category, but some people, when they go to watch 3D movies, they end up feeling sick. Right? They can't cope with it. And there are a couple of reasons for that, which we'll talk about here. So one of the problems is that, problems for some people, is that there's a decoupling of the focus and convergence distance. So what do we mean by that? Let's just compare seeing something in 3D in the real world and something in 3D on a screen. So in the real world, if we focus on the coffee cup, which is close by, then our eyes converge to a certain angle to both be pointed at the object that we're viewing. And at the same time, we are focusing at that particular distance. So they're two different operations. One is the angle of our glance from each eye, and the other is the adjustment of our lens to focus to that distance. And that distance is always the same, of course, because the coffee cup is at one fixed distance from our eyes. And then if we want to look at something a long way away, then of course we change both of those, right? Our point of convergence is somewhat further away, so the eyes sort of diverge a little bit, and our lenses adjust to a different focal length. But now if we think about what happens when we've got a screen and we're presenting multiple images for a 3D effect, then the point of focus is always on the screen, yeah? Because that's what we're looking at. That's the image is projected onto this screen. We're always focusing on the screen. But to get the 3D effect, however we're separating these images, whether it's by glasses or lenticular lens or whatever, we have a different point of convergence. So our eyes are converged as if the object was here, but we're focusing on something that's a different distance away, and the same thing in the case of the distant object. So for some people that's fine, but for other people they feel a bit like they're travel sick or something. It's just their perception is disturbed. Another problem or irregularity with 3D displays is the focal irregularities, and this is illustrated by the graphics here. So in the case of the real world, if we're focusing on this object back in the middle of that angle there, then these bits are out of focus, right? Because we're focused on that particular distance. But in the 3D display case, everything's in focus because we don't know where we're going to look, right? And so, and that's just wrong, right? If this really is a representation of an object that's shaped like that, then these bits should be out of focus if we're focused there, and this bit should be out of focus if we focus there. So this again can disturb some people, and it's actually interesting if you, I haven't looked at all that many 3D movies, but you see some in which the director deliberately defocuses parts of the picture to force you to look at what he or she wants you to look at, and it's kind of forcing that experience. Okay, so that's the perception of 3D. But how do we actually transmit it or transport it? We've got 4 more slides, I think. So we might just get in by 8 o'clock. There are 3 approaches that have been taken to transmitting 3D TV, or strictly stereo video. So stereo means we've got 2 channels, essentially. Let's think about those 2 channels. So one, where else would you see it standardized but MPEG? So MPEG has standardized multi-view coding, MVC. I mentioned it briefly many lectures ago, and you might well have forgotten, which is fine, because we didn't focus on it. But it was a method that was originally used, originally developed in MPEG 2, and has been carried through to the other standards, that allows some bandwidth reduction compared with sending the 2 views independently. We'll talk about how we do that in just a second. One of the features of that method is that it's compatible with 2D. So you think for a moment, what does that mean? Really, we're sending one 2D view, and we're using that to predict the other one. Right? So we're exploiting the commonalities between them, and providing compatibility for a 2D receiver at the same time. So it's actually a little bit like scalable coding. We've got a 2D channel, and we've got an enhancement channel for 3D. We'll look at more about that in just a second. What the other approach that's more common, I mean 3D TV is not that common these days, but where it's used, they tend to use this approach, which is that we take our 2 views and we do some signal processing to push them together, squish them, and make them look to the transmission system as if they're just one. I'll show this with a graphic in a second. The advantage of this is this point here. It's fully compatible with all the existing transport infrastructure. All your encoders are set up to encode 2D images, and that's what you're presenting it to. It just has to be separated out at the far end. And there is a third approach that has been used, and I include it only for technical interest because I'm not aware of it being actively used anywhere. Philips used to have a system that used it, but they haven't persisted with it. And the idea here is that we have a 2D image, but then an extra channel that tells you how deep each point in that array is. So that seems really attractive from the point of view of it being compatible with any display. We haven't just got two views, we've got a kind of a 3D model, and so we can look at it from any angle. But it's obviously not able to see, to represent anything that's occluded. Right? So if I have such a representation for an image that includes my phone here in front of this screen, I can show the depth of this point and I can show the depth of this point, but if I then try to generate a view from here, I haven't got any information from behind here, so I need to kind of interpolate or something. Let's use some graphics to illustrate what I meant by those other two systems though. This is the middle one on the previous slide, the left-right approach. So the way this works is that, of course, we've got a stereo camera. It generates our two views, but we use this video processing block here to just, as I said, subsample, filter and subsample the images, so we have a lower resolution, lower horizontal resolution version of each image, which might seem an ugly thing to do, but it's a sacrifice in resolution that we're prepared to make. But by doing that, we create this side-by-side image, which for all of our existing transmission system looks like a conventional image. And so we can encode it and we can transmit it, and all the transport stream stuff all works just exactly the same. 3D TV sets know how to decode this. I'm not sure if there's some side information that can tell them how to do it, or you have to set it in the setup, but they can separate out these two views and then show them to you using your LCD glasses or similar. The features of this approach, we've got a loss of resolution compared with 2D, of course, because we had to do that processing stage. It's only properly displayed on a 3D display, so we can't pull out a 2D version unless we do some special processing to extract just one view and then stretch it out again. And the delivery bandwidth is doubled if we have both versions. So if we wanted to do a 3D broadcast of a grand final event, sports, soccer or something, and we want to do it in 2D and 3D, then we need two channels, or we need twice the bandwidth, twice the bit rate. But the advantage is, particularly if you're at the early stage, you're a broadcaster and you're not sure if people really want 3D TV, and I think it's a big question mark just at the moment, then it's cheap because you don't have to replace anything in this delivery chain. Right? So you can try it out, see if anyone actually is interested in it. So this is the MVC, the multi-view coding approach that MPEG has standardized. And so the idea here is that we encode one stream as a base stream, a 2D view, which can be pulled off by a conventional decoder and displayed. So we have that compatibility. But we also provide this enhancement stream that allows the 3D capable display to take both streams and generate both views. The features here are that we can reduce the overhead because we're predicting one stream from the other, one view from the other, so we get some advantage compared with sending two 2D views. And it provides this compatibility between the the two receivers. But we not only do we need a new display, but we need a new decoder and we need a new encoder to support this. How does the MVC encoder works? Well, at a high level, it starts with a conventional form of encoding and prediction, as you might expect. This is just like a conventional 2D encoded representation. But for the other view, we take advantage of the correlation between the views by performing prediction not just in time, but also from one view to the other. So the view 2 encoding is done by predicting temporal direction, but also predicting from the other view. So we can, and it's doesn't involve significantly new protocols. We're using two vectors to predict the B picture. It's just that one of them happens to come from this other source. Okay, so what's the status of 3D TV? I really include, because it's not particularly popular, I really included it more from the technically interesting aspects. From the broadcaster's point of view, it's potentially differentiating themselves. Broadcasters are always looking for some way to be different from something else, like cinema in the past, or today it's internet, volume on the internet. But that's kind of temporary, because already you can get stereo video sources over the internet. There's limited resurgence, I suppose, of interest in 3D in the cinema, so that presents some opportunities for the broadcasters to use that material. But the 3D in the cinema is not taking off wildly either. It is a good argument for more bandwidth. There's always this tension between the broadcasters and the government. Broadcasters always say we've got to have more bandwidth, arguably what they're really saying is we don't want our competitors to take bandwidth, but they're always arguing for more bandwidth, and if they say they need to do 3D TV broadcasts and it requires lots of bandwidth, then that's a good argument. There are lots of barriers to 3D TV though. It's a major reinvestment. They've invested in HD already, and they're still trying to get payback probably. They see 4K on the horizon, and so it does involve significant investment if they wanted to go down that path, and user acceptance is not by any means certain. Of course, it requires the 3D capable displays, and there isn't really a standard. There are different solutions there, and consumers are still upgrading to a large screen HD TV, and maybe they're looking forward to the next step, which might be 4K rather than 3D. And I mentioned that there's uncertain user acceptance. The glasses are not popular. The glasses-free systems have restricted viewing positions, and some viewers don't like the experience anyway, and there isn't much content. There's limited content. Standards are now under development though, of course. MPEG has done the multi-view coding standard, and the SMPTE, the Society of Motion Picture and Television Engineers, have some standardization activities in that space. Anyway, it's a matter of personal opinion whether you think 3D TV will ever take off, but it just has some interesting technical aspects that I thought was worth including. And so that's finished that topic. So we're done for tonight. We see one another one more time next week. So next week we'll talk about digital cinema, I mentioned, digital cinema sound, and maybe some aspects of mobile multimedia as well. And I'll tell you all about the exam. I'll give you copies. Yeah. Sorry? Is
all lectures?
All lectures. All lectures are potentially examined.
Potentially doesn't mean all.
Well, you know, I've only got 3 hours in which to push you to the limit. So,
Different sub-bridge.
sorry?
Different sub-bridge.
No, I don't think that'd be a good idea. See you.
Question. We see some people drawing 3D picture on a wall or on a ground. It looks like very 3D stuff, but what's the difference between we're talking about here today, like the technology?
Sorry, what was the one you were mentioning?
We saw some people drawing some picture, like 3D picture, right? On a
Drawing,
wall.
you
Drawing,
say?
yeah, like picture. They on the ground or on a wall.
Yeah.
And it looks like very 3D.
Oh,
thing.
okay, right.
Yeah, right. So, what's the difference between the technology we're talking about here today and the
Oh,
one we
well,
thought?
that's just.
Because actually, it's 2D.
Yeah,
It's the
but it's
drawing.
just. Oh, okay,
Yeah.
but it's just playing with your perception because it looks like it's. I guess there are lines going off to infinity,
Yeah.
as if it really is
Yeah.
deep. But then if you move your location, you don't.
You mean a position?
Yeah, you move your position, then it
It
doesn't
won't be 3D.
doesn't behave as if
Okay.
as if there really was a corridor disappearing into the distance. You know what I mean?
Okay, right.
So with what we're talking about, we actually have two views. So if the camera moves position, then the parallax difference in
Yeah.
appearance shows us that there really is depth in the image.
Okay.
It's not just that it's kind of photorealistic.
Okay. Yeah. Because that thing, it doesn't require any extra device or something. We just look at the picture. and
Yeah,
see.
that's right.
So
Yeah.
I'm thinking if the video, I mean, maybe the company, they can like using this kind of stuff. You can require a customer just sitting in the fixed position,
Yeah.
and they display the video on the screen, and we can see the 3D stuff.
Yeah, but I don't think. But I
Yeah,
think.
I don't-
I think it's only because it's kind of a very clever drawing, a photorealistic
Yeah,
drawing.
yeah.
It's not genuinely.
But I
It
think
doesn't-
if
doesn't
we
contain
like,
genuine depth.
if we make all the like this kind of 3D picture in a series like as a movie,
Yeah.
like 20 frames in a second, actually it's a 3D movie, right? If you
Well-
doing that and you're sitting in your particular position, you are not moving to
Yeah.
you just
But-
sit here,
Yeah.
fix
But
it, don't move, and you can see exactly 3D movie.
uh,
Technically.
yeah, I'm skeptical.
Yeah, okay.
Anyway, have a
Thank
good night.
you.
See you.
Yeah.